Hey class, Adam Ward here. I want to talk with you this evening about the heat balance for a stream. This goes along with lecture 30 in your Chopra textbook. This is my second lecture about heat balances, and so you should have seen me end a recent lecture with something that looked like this, where I was treating inflows, outflows, and exchanges across the surface of this pond. What we're going to do today is focus in on that J, that heat flux, or heat per area per time, and see if we can understand how waters are interacting with their atmospheres to set their heat balances. And so to do this, we're going to take a look at the major gains and losses of heat to a stream. So if we picture a stream, we're going to look at 5 key processes today. The first is solar shortwave radiation. Right? And so this is sort of the obvious one. The sun shines, things warm up, and some fraction of that may get reflected off. So we're actually interested in the net shortwave radiation. So SN shortwave net. The second term that we're going to look at is going to be atmospheric longwave radiation. And so this is based on the Stefan-Boltzmann law. Basically the idea that if you have heat, meaning if you're above an absolute temperature of 0, you are radiating heat. Everything is doing that, including the air. And so temperature in the atmosphere is going to radiate heat down onto the surface. And of that, a small fraction could be reflected. Then we'll take a look at what happens in terms of the stream. And so if the atmosphere has heat and radiates it down, so too does the water in the stream have heat and radiate that back into the atmosphere. And so we've got that sort of long wave radiation back toward the atmosphere. That JC term, we've got conduction and convection. So basically diffusion and advection processes for heat that are causing a net exchange between the air and the water. And then finally in blue here, evaporation or condensation, phase changes, which also use energy or deliver energy to the system depending on which direction they take place. And I'll just note here in black, there could be any other sources and sinks as well. At the end of this lecture, I'll talk about what a few of those terms might be. But these 5 terms I've outlined on this slide are what we're going to work through tonight. So let's start with shortwave radiation. Ideally, shortwave radiation can be directly measured. If not, you can make estimates. Shortwave radiation is going to be sensitive to the current date and time, where you are on the planet. And then more local factors like cloud cover, shading, and how much of that incident radiation is actually reflecting away. And so just to give you a sense of why that matters, you've all probably got a good sense for this already. Of course, you go through a seasonal cycle. The sun is brighter and warmer in the summer, less so in the winter. The days are shorter as well. So shortwave radiation tends to be one of the least of our concerns because it can be directly measured or estimated. Typically, cloud cover shading are the two that we're going to have to struggle with a little bit more. Second term is atmospheric long-wave radiation, and so we'll do this in 3 pieces. The first piece is this Stefan-Boltzmann component. Again, the idea that if you have temperature, you radiate heat. You can see the formulation there. You plug in air temperature in degrees Celsius. That will be converted to kelvins. You're plugging in air temperature in kelvins, getting the difference from absolute 0 and multiplying that by the Stefan-Boltzmann constant. Given here is 11.7 times 10 to the minus 8th calories per square centimeter per day per degree Kelvin. Chopra gives you this constant in a few other units as well. Be very careful in this equation that you're keeping your units homogeneous. Now, that's the long wave radiation from the atmosphere back to the stream. A couple of adjustments we need to make. The first, shown here in black, is what Chopra calls atmospheric attenuation. The idea of atmospheric attenuation is essentially heat getting trapped back in the atmosphere before it can get down to the ground surface. And so in that term, you've basically got 2 variables to plug in. That capital A is a von Karman constant. It should be in the range of 0.5 to 0.7. Typical value to use is 0.6. And then you've got this lowercase e subscript air. That is the vapor pressure in the atmosphere, or the partial pressure of the atmosphere that's due to water vapor. Chopra section 30.3.2 talks you through some of the finer points, ways that you can estimate this from relative humidity and air temperature. And finally, shown in orange is this term 1 minus RL. This is to deal with the reflection. And so the idea that not all of that long wave radiation that hits the surface of your water body will actually be absorbed. Typically about 3% of it is going to bounce back off without being absorbed. And so what you're doing there is multiplying functionally by 0.97 or 97%. So those are two of the typical sources of heat, so places that heat is getting in. The next three we'll look at are places where heat is typically getting out of our stream system. So our atmospheric radiation is a function of air temperature and humidity. Let's look at water long wave radiation. So this is BR, or back radiation from the water back to the atmosphere. Again, you can see that formulation looks incredibly similar. You've got your surface temperature for water. You've got your Stefan-Boltzmann coefficient, or constant. And this epsilon out front is the emissivity of water. And we're going to typically take a value of about 0.97. So this has to do with the ability of water to transmit its heat back to the atmosphere. So this term's not too bad. Conduction and convection. Functionally, those are diffusion and advection for heat. And you can lose heat across that interface by both processes. So our model is going to look like this. We'll go through it piece by piece. On the far right, surface temperature of the water and temperature of the air. You've seen that. This FUW is what Chopra calls a wind function. That's defined as 19, which is the conduction piece, and then 0.95 times UW squared, the convection piece. And that is relating to the wind measured 7 meters above the water surface, plugged into that equation in units of meters per second. We've seen something like this before when we looked at mixing in lakes, and we looked at liquid film and gas film controls and surface renewal theory. These exchanges being proportional to a wind speed squared is fairly common for us. And finally, out front, Bowen's coefficient, 0.47 millimeters of mercury per degree C. So that's a pressure on top and a temperature on the bottom. And those are the units that you should be using in this equation. Final term deals with evaporation or condensation. So if you find that this term is negative, you actually have a net condensation, or a transfer of energy into the system. We've written the equation assuming that this term will be positive, and so that it would be a net evaporative loss of energy from the stream back into the atmosphere. You've got your wind function again, and then you're multiplying that by the difference between the actual vapor pressure, E air, and the saturated vapor pressure, E sat. And again, if you take a read through Lecture 30 in Chopra, he walks you through where you can calculate these based on humidity, relative humidity and temperature in the atmosphere. So pulling these things all together, what we've spent quite a lot of time doing in this lecture is getting these 5 terms that basically do the heat balance across the surface of a water body. You can apply that to CSTRs, plug flow reactors, mixed flow reactors, all the fun things we've done all semester. I wanted to just take a second and talk about a few of those sort of other terms that you might think about. Is heat loss to your stream bed important in your problem? If so, perhaps you want to add another term that would be a conduction or convection term that would describe the losses of heat down to the earth, which would basically sort of act as an infinite sink. One of the more interesting cases that I'm aware of, and I'll share a paper in our class files with you all from a gentleman named Martijn Westerhoff. Martijn was working in a very small stream that had a lot of large rocks that protrude out of the water. And in his stream, he couldn't get this balance to close without accounting for conduction of heat from the sun to the rocks, let them heat up during the day, and then they slowly cool down overnight and transfer their heat back to the water. So this is the first time I've ever seen that process modeled in a paper, but I pointed out here as yet another source or sink term that one could add to their heat balance if things weren't closing. So anything that you can describe as a source term or a sink term using a heat flux, again, heat per area per time, you can add into this problem. So having watched the previous lecture and this one, you should be comfortable describing these 5 processes that move heat either into or out of a stream channel. You should be able to work through the equations to calculate the magnitudes of each of those, come up with a net heat exchange flux, so that J that doesn't have any subscripts, right? Sort of the net exchange term across the surface. And you ought to be able to use that in any of the heat balance equations that we've done in the past. So in particular, you could test yourself by writing these equations out for a CSTR and make sure that you would be comfortable building that heat balance equation. Thanks for sticking with me, and I'll see you all in class. Have a good night.